Hello, everybody. Welcome to the last MagX of the season, of this year. We've had, of course, it was on the fourth Tuesday instead of the third because of the Thanksgiving week. And we're not going to have one during Christmas. So we'll start again on, I think it's January. I forget, I have to look, third week in January. So what we have today is we have Ryan Baumbach giving the talk, and he will be introduced, and the discussion will be led by Kaya Wei. So take it, Kaya.
Thank you, Laura. Good afternoon, everyone. Welcome to today's MagX presentation. Our speaker today, Dr. Ryan Baumbach, is a research faculty 2 at the National High Magnetic Field Laboratory and an associate research professor in the physics department at the Florida State University. His PhD was completed in the Department of Physics at the University of California, San Diego, after which he was awarded a director's postdoctoral fellowship at the Los Alamos National Laboratory. His research group focuses on investigations of emergent magnetic, electronic, and superconducting states in crystalline materials. This prominently includes F-element systems and materials with novel electronic topologies. In all of these efforts, Ryan leverages his advanced material synthesis laboratory, bulk electrical transport and thermodynamic measurements, and measurements in high magnetic fields. He serves as a research mentor for a diverse group of undergraduate, graduate, and postdoctoral researchers. He also serves as a member of the Graduate Affairs and APS Bridge Program committees in the FSU Department of Physics and on the MagLab Diversity Committee. To promote broader educational efforts, he annually hosts research experience for undergraduates and teachers and participates in K-12 public outreach activities. Now I will pass it to Ryan for his presentation. There will be 20 minutes presentation followed by 10 minutes open discussion. During the presentation, if there are questions that will add to the discussion, please feel free to interrupt. Otherwise, please wait until after the presentation. Whenever you're ready, Ryan.
Okay, thank you, Kaya. I'm going to go ahead and try and put this up on the screen. Hopefully I've got it. And I'm going to put it to full screen. Let's see. There we go. Okay. Does that look okay? Okay, thank you. Well, thank you for the introduction, Kaya. It's really a pleasure to be here and to be able to give the last MagX talk of the year. And the title of this talk is Crystal Synthesis, Enabling and Benefiting from High Magnetic Field Experiments. And in this talk, I sort of want to circle around 3 main questions. And I don't claim that I'll be able to answer them all for you, but I hope that I'll be able to at least give you a flavor of what we think about when we're trying to answer these questions. And this includes things like, how do we even choose what we want to grow? Where are we going to go in the chemical structural phase space? As we're doing this, what synthesis methods are the ones we want to use? What do we have available to us? And, when and where are magnetic fields useful in the synthetic efforts that we want to undertake? All right. So with all that in mind, the place that I want to start is just to say that one thing that really distinguishes modern society, from how things were even 100 years ago, is that we have all sorts of materials that are optimized to lots of specific tasks, right? And these can be biomedical, engineering, construction, so on and so forth. But an important subclass of these are quantum materials. And so a quantum material is one where the wave-like character of electrons sort of takes over and rules the day in terms of what we see. This is combined together with the presence of quantum spins, structural effects, orbital degrees of freedom. And in these sorts of materials, these different factors are combined in ways that produce really novel phenomena. And something that I've heard said before, and I think it's a nice way of putting it, is that each class of quantum materials and each individual quantum material is really a universe unto itself. So while other branches of physics, like particle physics or astrophysics, have one universe to study, we have thousands and thousands, and some of them are much like each other, and others are very different, right? So this is very exciting and a wonderful way to drive basic science. But that's not all. We actually get something else too, and that is that quantum materials actually have applications as well. And I've made a sort of arbitrary distinction between types of quantum materials here. I'm talking about classical quantum materials, quote unquote, and next generation. And what do I mean by that? Well, classical quantum materials, at least in my mind, are ones that we've known about, maybe for decades, and we've come to some understanding of the basic science, and we're able to implement them in a variety of different settings. So for example, superconductors are critically important for medical MRI, particle accelerators, and other places. Semiconductors are for computers, permanent magnets, so on and so forth. Okay. Next generation quantum materials are sort of the ones that are at the leading edge, things that we don't fully understand yet, but we believe or hope will also have incredible applications in the future. And this includes things like materials with protected topological states. You might make qubits or do quantum teleportation or make quantum sensors. Two-dimensional electronic systems in the quantum flatland are exciting. And my own area of expertise is in strongly correlated electron systems, and especially now, examples that also mix this with protected topologies and frustrated ground states. All right, so the big picture is that quantum materials have the ability to drive basic science, and they can also give us very useful applications. But the fact of the matter is that we're faced with a huge structural chemical phase space. And even if all of us here at the MagLab dropped everything and went out and immediately started growing materials for the rest of our lives, we really wouldn't paint out really very much of that space, right? So we're immediately faced with a really serious question, and it's one that people have dealt with for decades, and it's just the question of how do you choose what to grow? This is a challenging problem. And in order to tell you how we do deal with it, I'm going to just focus on a really small subset of materials as a stand-in for all other families of materials. And that's materials that are formed with elements coming from the F shell. So just to remind you, the F elements are the ones that are located at the bottom of the periodic table. They're listed here in the bottom right-hand corner. And what's special about these elements is that they're so deep in the periodic table is that where you've already been able to fill up the S, P, and D orbitals, and you finally made it to the F orbitals. And what distinguishes those F orbitals is that they tend to be very close to the nucleus. And not only that, but they're sort of embedded beneath other S, P, and D shells. And so this makes them different from other elements in that they hold on to their spin quantum number because the electrons are well localized, and they hold on to a good orbital quantum number. And the result is that they are a good place to find magnetism, and they're a good place to find anisotropic magnetism. So when we think about F elements, and this is definitely what people thought, in the middle of the 20th century, they thought we're going to find magnetism. And in fact, there's thousands upon thousands of magnetic intermetallics that contain F elements. And maybe a highlight of this that's worth pointing out is, for example, the neodymium iron boride permanent magnet that's just ubiquitous in technologies. All right, so we can say, what do we want to grow? Let's grow magnets. Okay, let's use F elements. And that works. But actually, there's much more to this. And there's a big surprise that came almost right away as people got serious about studying these sorts of materials. And that is that in addition to having these well-localized F electron states, they can begin to interact in really novel ways and very strongly with their environment, with conduction electrons that are around. And so immediately there were big surprises. This starts in the 1960s, picks up steam in the 70s, and continues to be an ongoing area of research. A prominent example of this is that for some F elements, there's the capacity for the F electron states to mix strongly with the conduction electron states. When this happens, one possible outcome is that you can have something called a Kondo lattice that leads to a heavy fermion ground state, where there's an incredible behavior that you observe Fermi liquid behavior, but the charge carrier quasi-particle masses can be several hundreds or thousands of times that of the bare electron mass that you would see in a regular piece of metal. This is an incredible mini-body type of physics. Furthermore, amongst these sorts of materials, there are even unconventional superconductors. And in these superconductors, the pairing mechanism to form Cooper pairs is thought to not be phonons, as you would see in a classical or conventional superconductor, but perhaps something else like magnetic spins or correlations. And nobody really knows, I don't think, with absolute certainty. right? And beyond this, there's even examples that exhibit even more exotic electronic and magnetic states, such as uranium, ruthenium-2, silicon-2, which has something called hidden order. It's a mysterious ordered phase. The point being that there are states in these materials that are at the edges of what we understand, and they push theory and experiment. Okay, so what's the big picture? The big question I'm trying to ask is, how do we decide what to study? Well, one way that we can do it is that we can make an intelligent decision about where to go. Let's study magnetism, and then start turning over the dirt, right? Let's start making things. And what this does is it opens the room for serendipity to intervene. And we know that serendipity is a viable path to discoveries, at least in these sorts of systems. Okay, so this is part of the story, but there's another part. And that is that sample quality matters, and it matters a lot, okay? And I want to tell you a really quick story about a material that has been studied quite a bit now here at the MagLab, and that's the strongly correlated system uranium-tellurium-2. People are interested in this because it's an unconventional superconductor where you can apply a large magnetic field and destroy the superconductivity, and then you can apply an even bigger magnetic field and the superconductivity comes back. This is bizarre, okay? And that's a whole other story, but that's not the story I want to tell right now. What I want to tell you about is in this left-hand graph, where you can see the electrical resistivity versus temperature for a variety of different samples. And I first want to focus on the upper curve, the one that's in gray, that says low quality, no superconductivity. Okay, the first time this material was made and studied in this way was in 2006 by a group in Japan, where they produced these materials using something called a self-flux method. It doesn't really matter what that is, it's just some way to grow the crystals. They grew them, they measured them, they saw that it was kind of a bad metal and no superconductivity. So they did what anyone would do and they moved on, right? We don't want to spend a lot of time on materials that don't look very interesting. But something shocking happened in 2019, and that is that Sheng Ran and co-workers, I think serendipitously, because they were using a different crystal growth technique, actually produced this material again. They were using an iodine vapor transport method. They measured it, they found that it was a better metal in this case, and lo and behold, it exhibits superconductivity. This kicked off a very intense period of research, part of which was trying to improve the sample quality. That happened to a certain extent using this iodine vapor transport method. But again, just this year, there's been a new revolution in how to produce these materials, where a molten salt flux method has been brought forward by Haga and co-workers. And now we find the lowest residual resistivities, the highest superconducting transition temperatures, so on and so forth. Okay, so what's the point here? The point is that yes, we can go in the phase space and look for different combinations and discover things, but also we need to think about this axis that is really just how good is the crystal, right? And that's a separate axis from just prospecting around out in the space. Okay, so that's, in a nutshell, the challenge of developing new materials. And in order to do this, we need to have familiarity with the fundamental degrees of freedom. Are we going to set out for magnets? Are we going to set out for, I don't know what, whatever you like. You have to have a rational direction. But as you do this, you need to have a deep knowledge of chemical, structural, electronic, and magnetic trends. And you must sift through the chemical and structural phase space. That's a proven way to discover new things. And the reason that we do that is that we want to create space for serendipity. And as we do this, we have to maintain a commitment to refining sample quality. Okay, and in practice, what does this mean? It means that this work is all surrounding physics, chemistry, and material science, which must work in harmony. That's the key to success. Okay, so we're going to do this. We're going to go out into the periodic table, and we're going to take advantage of the quantum materials foundry, right? And so to start with here, I want to make the comment, that in physics, we learn about the hydrogen model and then the helium model and building out shells and so on. And this is very powerful, but it's not exactly the perspective that we want to take. Instead, I think it's important to look at the periodic table and think about the different personalities, electronic or magnetic, that different parts of the periodic table might offer you. Some will be more metallic, some will be more insulating, some will give you more spins, so on and so forth. But because we actually want to make things, we also have to think about the actual physical properties of these things, right? Different elements have different personalities. Some of them have very high melting temperatures, some are low, some are poisonous, some have high vapor pressures, some are radioactive. We have to have mastery of all of this. And as a result, different growth methods must be tailor fit to the desired products, right? And this is a key part of this loop between physics, chemistry, and materials science. And it's exactly this that our different quantum materials design and synthesis groups at the MagLab, this is the path that we're all following. And I'd like to say that this is our loosely affiliated quantum materials design and synthesis group. If I have excluded someone, it wasn't intentional. Please just send me an email and I will add you to the list. But in any case, here is at least a nearly complete list of people that are doing this. And I would think it's fair to say that all of us are following a path that's laid out in a really wonderful review paper by Paul Canfield, where we are making materials, we're measuring them, and we're tuning them. And we're trying to close this loop as many times as possible and as rapidly as possible, because we want to get over as much of that chemical phase space as we can. In order to do this, we're using a variety of different crystal growth techniques. This is just a schematic showing how we can do things. All of these things are possible here at the MagLab, and it includes methods like solution growth. If you've ever grown sugar crystals, maybe in school or maybe with your kids, you've done this, except that we like to use higher temperatures and things like molten metals or salt fluxes to grow our crystals. Many groups are also very good at vapor phase growths. This includes using things like high vapor pressure elements like iodine, which can act as a sort of conveyor belt for moving elements around and constructing crystals. We have groups that are specialized in thin film techniques, Christiana Beekman with pulsed laser deposition, and Wang-Q Park and Laura Green with magnetron sputtering. Luis Belikas's group are experts in exfoliation of materials, stacking, and building of devices. And then finally, we have capabilities for melt growths, right? So we can do things like melt things with arc furnaces or pull crystals using the Bridgman, Czochralski, or float zone techniques. Okay, so what does this mean? At the MagLab, we have this effort. We can drive basic science, we can generate intellectual property, but we also do important things for the users, right? And this includes making sure that well-characterized samples are available to users and collaborators. We maintain materials handling and processing expertise for users. We ensure safe handling of hazardous and radioactive materials. And I think very, very importantly, we're engaged in educating and training students, and students that have these skills are very marketable, after their PhDs or undergraduate degrees. All right, so that's what we can do in a nutshell. Now I want to ask the question, can magnetic fields open new areas for material synthesis and processing? And I think, and I want to show you that the answer is yes. I think this is a very exciting area that we should go into, and we are fully capable of going into. So let me tell you a little bit about that. First of all, we're not alone in thinking this. International efforts are already underway. And this prominently includes activities at the High Magnetic Field Laboratory in Hefei, China, as well as in the EU, for example, in Grenoble, and in Japan at the National Institute for Materials Science. This is an early stage field. It's not as well developed as many others. So you can actually go out into the literature and possibly read everything. I wouldn't claim that I've read everything, but you can get pretty close. And you start to see some trends emerge as you do this. This includes that magnetic fields are a great way to control the microstructures of alloys. And in fact, there's a large multi-institution project that James Hamlin and Mark Meisel are involved in. It's funded by the Department of Energy that's looking at this in manufacturing steels. Magnetic fields are used to manipulate nanostructures. And one that I think is especially intriguing is that magnetic fields can be used to produce metastable phases, metastable structural phases. That's shown in this publication that's at the bottom of the page here, where an investigation was made of some dichalcogenides, like molybdenum disulfide and tungsten disulfide, where hydrothermal synthesis was undertaken under varying fields. The main outcome of this paper is that if you do this in molybdenum disulfide or tungsten disulfide, You can convert the crystal structure from the one on the left, which is called 2H. I don't know why it's called 2H, but it is. You can convert it from that to the one on the right, which is called 1T. And why is this important? Well, one of them is more of a semiconductor, one is more of a metal. And I think people are probably familiar that amongst the dichalcogenides, there's many interesting band structures and there's many interesting superconducting examples. So this is a way to open up new routes, in this family of materials. And I think beyond this, we should be asking the question, if we can do this in this kind of simple situation, what more can we do in more complicated structural chemical arrangements? Okay, but the story doesn't end there. Another place where this is important to consider is that if we consider the relative energy scales between a magnetic field and temperature, we kind of naively have this idea that a Kelvin is a Tesla. But that's only really true if we're not thinking about the G factor. So amongst lanthanide elements, where you can have a G factor, for example, as large as 5, then in a field of 18 Tesla, that energy scale gets to be more like 60 Kelvin. And if we're doing our growths between 500 and 1,000 degrees C, this starts to matter. It's a new axis that we can add to our phase diagrams where we might actually uncover new phases of materials. Other important impacts, if you think about a melt, there's a lot of free electrons. And the result is that the melt will sort of travel around the applied magnetic field that will interrupt natural thermal convection. And I think that'll have an impact on crystal growth. And then finally, you can easily imagine that there are things related to preferred growth directions. Okay, so how are we going to do this? Well, we actually have activities underway already. This is a schematic at the developing high B times T facility down in Gainesville, where Mark Meisel and James Hamlin are sort of taking the lead. There's a lot to say about this, but I just want to emphasize that at the moment, they've already put together a 9 Tesla system that's coupled together with a 1100 degree C furnace. And we're carrying out experiments with them as we speak. All right, one of those early experiments is shown here. This is an interesting idea where if we consider the binary phase diagram that's shown in the upper left-hand corner for cobalt and sulfur, you can see that the melting line, which is illustrated by the separation between the white area and the purple area, if you go into the right concentration range, this melting temperature drops significantly. And in fact, it drops below the Curie temperature of cobalt. So now you have the opportunity to grow cobalt crystals within the ferromagnetically ordered state. What will this do? We don't actually know. But you can see that it has an impact. That's illustrated on the bottom of this slide, where crystals grown in 0, 3, and 9 Tesla, as well as a 9 Tesla gradient field, clearly have different morphologies. So what does this mean? Is there preferred orientation of crystallites? Does it impact magnetic properties? What about electrical transport properties? We don't know. But just imagine, if it can do this in a simple material like cobalt, where the spins are actually not that large, what more could it do in more complicated systems? I think this is an exciting question to ask, and it's wide open. All right, so that brings me to the end. I'll just summarize with my perspective. I think that the search for new quantum materials remains exciting and unsolved. Like I said, this really requires working at the interface between physics, chemistry, and material science. They have to work together in harmony. And this is a wonderful training ground for the next generation of scientists. Our students who work here are very marketable. I think that's a great thing. And then finally, thinking about magnetic fields and synthesis in high magnetic fields, I really do believe this is an untapped opportunity that we're ready to move into. So with that, I'll say thank you and just gladly take any questions.
Thank you, Ryan. That was a fantastic talk. Now we're open for discussion. If anyone has questions, please feel free to unmute yourself and just go ahead and ask.
Hey, Ryan, it's Lance.
Hi, Lance.
Back when the BES, DOE BES, pushed the sort of materials genome into synthesis activity, modeling, density functional theory was also sort of part of the run up into material by design, into property measurement and so on. What modeling is going on?
Yeah.
I mean, I'm thinking of like Warren Pickett, for instance. He had all sorts of crafty programs there.
I certainly agree that modeling is important. I think it does especially well. I mean, it does incredibly well in systems that don't have strong electronic correlations. So my understanding, and I'm not a theorist, but my understanding is that when it's a single particle type of situation, this is okay. But as soon as we bring in strong electronic correlations, this becomes challenging. And I believe you have to use something called DFT plus DMFT to try to account for this. There are groups worldwide that are doing this. I know that Vlad has spent time on it. The person's name at Rutgers isn't coming to me, but there's a well-known theorist working there. Kotliar, that's right. And it's not straightforward. It's not straightforward, but I think it's important.
Yeah, Laura, it'd be great to get a seminar on the latest in modeling of Fermi pockets and, topological correlated behavior in that. So, okay, my request is passed.
EFRC that worked on that, and we kind of, when we talk about predictive materials by design, we also have to go ha ha ha, because it really is complicated. But with the group here, it's time to bring some other people in, and
I think that's right.
Yeah.
So I have spoken with so many people, colleagues here, who would love to have a band structure person who we could work, hand in hand with.
Okay.
That would be very powerful. Yeah.
Great question, Lance. I have a question too.
Oh, please.
Okay. So there's an idea that's been kicked around and keeps being dropped, and now it's being brought up again, which you may remember. There were these handbooks of superconducting properties by Roberts.
Absolutely.
There were 3 volumes, okay? And every once in a while groups, so what these were these little volumes, which you could look up, niobium 310, when it was discovered, what its properties were, etc. And they would update it, and that hasn't been updated in decades. So some people talk about redoing that again, putting in the materials that failed. In your opinion, Ryan, is that a bad idea?
No.
Because just like you showed of something that was grown 20 years later, looked totally uninteresting.
Yeah.
Do you think that will talk people out of trying to regrow materials that looked boring before?
So I have a lot of thoughts about that. And the first one is that amongst crystallographers, they're already completely committed to this type of idea of making easily accessed aggregated data, for example, in the ICSD. And it's very powerful. We all rely on it.
Right.
That's one statement. A second statement is that I actually do not believe that you can make reasonable choices about what to make without knowing the broader behaviors of a family of materials. In other words, I think that if you know that there's a large family of materials, you should attempt to create a map, right? And I've done that actually in a recent publication where we did something very simple and just tried to make a map that relies on unit cell volume and shell filling. I mean, this is incredibly crude. And yet, at least amongst the family of materials that are crystallizing with the thorium chromium 2 silicon 2 structure, which is a huge family of materials, for the F electron intermetallics, it organizes them very well. And then you can see, if it has a certain unit cell volume and a certain electronic shell filling, will it be magnetic or non-magnetic or possibly even in the crossover zone? And we all know, well, I don't know if we all know, but there's a field of science that's interested in these crossover zones from magnetic to non-magnetic behaviors. This is thought to be quantum critical behavior. And it's exactly here where we find a lot of unconventional superconductors. So I think it's really useful to aggregate data and to try to organize it in ways that are not, they're Hamiltonian informed, but it's not writing down a Hamiltonian. It's writing down a phenomenology. And then we try to make use of that. I mean, Matthias did that, and had great success. Obviously, we need to go way beyond that, but I think that's a very smart thing to do. Yeah.
Okay, it's a great take on that. Thank you.
Any other questions?
Yeah, I was wondering, how long do your samples last? And can they be used by other groups? And do you have a collection of lots of different samples?
Fantastic question. So the answer is it depends on the material. Uranium tellurium-2 is very susceptible to moisture, air, so it degrades. Even if I seal it under vacuum and store it in a quartz tube, it just degrades. That material is very, very sensitive. Other ones, we grow all sorts of silicides and aluminum things, and other ones will last forever. So it really does depend on the particular chemistry of the material. And yes, we have built up a sizable library. And there are even other libraries, like there's one at UC Santa Cruz that Art Ramirez has that came from Bell Labs, which is enormous. And speaking to this question of should we be aggregating data, I think we should also be aggregating materials. And there should be a national repository for materials that you can just comb through. There should be an online database you can comb through, so we don't have to duplicate these efforts over and over and over again. That seems like, counterproductive to me.
All right, I see one hands up. Please feel free to unmute and ask.
Okay, I have a question. From all the methods to grow crystals, which one is most adapted to be done under a magnetic field?
That's a great question.
Because a floating zone method,
Yeah,
I guess there's only the split magnet that could be used.
I think you're absolutely right. Well, so I think you want to start as simple as possible. That would be my preference. I would want to start as simple as possible. I do think that a clever person could probably implement any of these, given enough time and money. But I would say start simple. And so what we're doing with the tube furnace that's now working at UF is we're mainly focusing on these molten metal flux growths, because all we have to do is seal the sample inside of a quartz tube. We can make pretty small quartz tubes and then just slide them inside of the tube furnace. Or we're also doing some vapor transport growths. And I think that just by focusing on these, without going any further, we're going to have lots of opportunities for progress.
I have another question. So when I did my master, I was trying to get a semiconductors that would be doped with paramagnetic species in order to have it ferromagnetic.
Yeah.
I was wondering if actually doing the same, like using the furnace and just doing ceramic sintering, could also be something to explore.
I love it. Yes, I agree. And that's, I say do the simplest thing, and I think that would be straightforward. Yeah.
Thank you.
All right, I think we're running out of time. If you have more questions, please feel free to take it offline. I will pass it back to Laura.
Well, I want to thank everybody for attending. That was a super tremendous talk. I loved it. And it will be posted online in a few days, and feel free to share, and feel free to also continue to ask questions and learn more about the MagLab and even your own area. So thank you very much for attending, and we'll see you in January.